Hello everyone, it's a few minutes past 11 and it's time for an Econ seminar on a Thursday. Welcome to the 2023 Econ Seminar Series and thanks for coming and thanks for the people online for tuning in. It's an honor and a pleasure for me to introduce Dr. Freja Østerstrøm. Did my best there. Freja did her PhD at the University of Copenhagen, Denmark, including collaborations with Ford Motor Company at Anchor. She focused mostly on laboratory gas phase kinetics and product studies of CFC and alkanes, CFC replacements and alkanes. During her postdoc in the UK and the US, she has combined laboratory work with modeling, first at the University of Leeds and then at the University of York, where she used an indoor air chemistry box model based on the MCM to model indoor air following a cleaning event in a house. Currently, she's a Marie Curie Global Postdoc Fellow at Harvard University and University of Copenhagen, where she's investigating the influences of stratospheric ozone by using both theoretical and experimental techniques in the form of laboratory halogen kinetics, spectroscopy, and 3D chemistry climate modeling of volcanic eruptions, which is, that is what she's going to talk about today. Before starting, I'd like to remind the people online that you can enter your questions in the space below the video at any time during the talk. At the end of the presentation, I'll be reading the question to Freja. And with that, I'll leave you the floor to Freja. Thank you.
Thank you. And thanks for letting me give us a talk here. So I prepared a talk with the title of How does Stratospheric Ozone Respond to Explosive Volcanic Eruptions? And I will go through a couple of examples of how this happens. So first, I want to talk about what is the deal with stratospheric ozone and volcanic eruptions. And then I'll describe the 3D model that I'm using, and then show you some model results for different projects that we did with this model. So first off, just to remind everyone, the stratospheric ozone layer protects the Earth from harmful UV light, and even a small change in ozone layer thickness can increase UV quite a lot at the surface. So therefore, we're interested in knowing the causes for ozone depletion. The success story of the Montreal Protocol is one of the biggest successes in environmental protocols. And we banned, through that, ozone-depleting substances, including the CFCs and some of their replacement compounds. But even so, some of these compounds, they still are around in the stratosphere. They're really long-lived. And we have ozone holes still occur seasonally on both poles. So what about volcanic eruptions? How common are they actually? So this was surprising to me, is that every year there's around 70 active volcanoes, and there's about 25 to 30 new volcanic eruptions starting each year. This also means there's about the same amount finishing their eruption. And one way to look at these volcanic eruptions, because they don't all make the news, they're not all big. So we can discuss the magnitude of their eruption using something called a volcanic explosivity index that describes the magnitude of an eruption. And these go in like numbers from like 1 to about 8 is the usual numbers that we're discussing. So something with a VEI 4 occurs roughly every 10 years. An example of this was the Eyjafjallajökull eruption in Iceland in 2010 that shut down a lot of the airspace over the northern hemisphere. And then the largest size is VEI 5 that occurs roughly every 20 years. And an example is last year's eruption of the Hunga Tonga-Hunga Ha'apai eruption. The next scale up is the VEI 6 that occurs less frequently with about 50 to 100 year time scale. And this would be, the recent example is the Mount Pinatubo eruption of 1991. And this is really the eruption that we observe with satellites and that most people are comparing to, because this is it's the biggest one that we have good observations for. The next size up is then we go into what's called a super eruption, and that's VEI 7 that occurs every 500 to 1,000 years. And the latest one we had was the Tambora eruption in 1815 that we have historical records of people discussing 1816 as the year without a summer. Tambora is in Indonesia, and some of these historical records are from the northern hemisphere. So it's just showing that some of these impacts are global. So people at the time, they didn't know there was a volcanic eruption on the other hemisphere, but they could observe that the summer was colder the following year. So some of these volcanoes are located around the Pacific, sort of at the rim of the Pacific tectonic plate. Just highlighting the Philippines over here where Mount Pinatubo is located, and here is the Tonga Trench where the Hunga Tonga eruption took place. So this is just an example showing that they kind of follow where the tectonic plates are, and then there's other types of volcanoes as well. So when a volcano erupts, we have hot lava going into the atmosphere that is relatively cool, so there's a drastic temperature change. There's change to composition, there's all the gas components that get ejected, water, CO2, SO2, and these all cool down and go through all kinds of chemistry, some of which would be the bromine explosion, like we know for like the polar spring events, for instance. And then this sort of thins out into a plume, and other chemistry can take place here. So one of the main gases that we talk about for volcanic eruption is SO2. But along with SO2, some eruptions inject halogens into the stratosphere. And examples of this is the Hekla eruption in year 2000. It had an enhancement of 80 ppb of HCl in the cloud, and 70% of this actually made it all the way to the stratosphere. And this was not a big eruption. For Hunga Tonga, the estimates are a little more fuzzy in terms of measurement, but there's at least less than 10 ppb of HCl, even though it was a bigger eruption. So it really varies a lot depending on the type of eruption and the type of volcano. The SO2 that is injected or ejected from the volcano will end up as sulfate particles, and they will cool the surface of the Earth. Following the Pinatubo eruption, we had about 1 degree cooling that lasted for about a year. And if we look at the amounts of SO2, the Pinatubo eruption was somewhere between 12 to 20 teragrams of SO2 that reached the stratosphere. And in comparison, Hunga Tonga was 0.4 teragrams. So there's quite a big difference in the magnitude here. And for what I'm showing, I am looking at what happens after all these gases enter the stratosphere. That's my starting point. So I'm bypassing a bit of the initial plume chemistry. So this is an example of a 2D model showing an eruption in 2018 in kind of a Pinatubo latitude. So in the main panel here, ozone loss is shown in red in percent over time. And then what I have at the top is an average overall latitude. And then on the side here, there's an average overall time. And then the number here shows the average of the entire main panel, so the global temporal average. And really what this figure is here to show is that when we have a volcanic eruption in a contemporary atmosphere, when this paper was published, this was the future. The paper was from 2017. We see a massive, widespread ozone depletion following a volcanic eruption. And this is due to the background chlorine or halogen content, or we talk about this as effective equivalent stratospheric chlorine that we still have around from the CFCs and related compounds. And in the future, this will decrease, and we're expecting that a volcanic eruption will have a different impact on ozone, potentially a smaller impact, but this all depends on things like the climate scenario we look at. So if you have more greenhouse gases in the atmosphere, this will reduce the risk to the ozone layer from volcanic eruptions. And this is just due to the fact that these greenhouse gases will react with the background halogen. So there's less halogen available to drive these catalytic ozone depleting cycles. And these mechanisms are enhanced by the volcanic particles. So that's really the driver, is that we have the halogens, and then the volcanic particles add the surfaces for heterogeneous chemistry. Another thing we can see is that if we have a co-injection of halogens, this will always lead to ozone depletion. So this would just mean the eruption itself supplies a bunch of halogens that can drive this chemistry. And this is seen for different climate scenarios and different model years. So moving on to the model I'm using, it's called SOCOL AER, and it's a model that's focused on stratospheric chemistry. It has an aerosol module that includes microphysics, aerosol microphysics and microchemistry. And the specific version that I'm using includes our implementation of how to do the volcanic injection and also boundary conditions based on climate scenarios. And then we're doing some heat fluxes to include a mixed layer ocean in the model. It has a T42 spectral grid, so this means it's got 2.8 by 2.8 degrees horizontal resolution at the equator, and we have 39 vertical levels spanning the surface up to 0.1 hectopascals, and then every time step for dynamics and chemistry are 15 minutes. And the overall structure of it is that it works in different modules. So there's a climate meteorology module that is fully coupled to the chemistry model that's coupled to the aerosol module. And then for the oceans, we can include this mixed layer ocean, and we have a bunch of boundary conditions that we're inputting, so prescribing those. So in specifically, it's ECHEM5 metrology coupled with meson chemistry, and then the AER part is the AER 2D model that's been coupled to the 3D model. And in this case, I am using the mixed layer ocean. And my boundary conditions are based on climate scenarios. So looking at some of the results from this, we did a study looking at the dependence on latitude, season, and halogen content of a contemporary explosive volcanic eruption. So the setup for this was using a climate scenario from the SSP scenarios. So this stands for shared socioeconomic pathways. So they're a combination, kind of the RCP scenarios with the social economic pathway of different versions of fuel use and collaborations between nations, economic growth, all those things kind of go into these. And I used the SSP 370, so that means it has a radiative forcing of 7 watts per square meter at the end of the century. And then it's SSP 3, which is I guess in some ways it's the worst case scenario, but at this point, I'm not too far off into the future, so all the scenarios are very similar. I'm running the model as 30 model ensembles, where I'm varying the CO2 within the range of plus minus 1% with a random number. And then for the eruption scenarios, I'm looking at 6 different latitudes of eruption, spanning 58 degrees north to 50 south, and having an eruption occur either in January or July of 2025. I used a vertical injection profile that was the same as the Mount Pinatubo eruption in '91, and then I had 3 different scenarios for the amount of injected volcanic species. So I have one that is SO2 only with 5 teragrams of SO2, and then I have 2 including HCl and HBr at either an intermediate or a high level. And the high amount of halogen are based on the SO2 to HCl ratios from the Mount Masama super eruption. And then we've scaled that to the amount of SO2 that we're injecting. And then our intermediate level is a factor of 10 smaller than that. It's an order of magnitude less halogen. So for the latitudes, we looked at a map along the west coast of the Americas, and so here I'm showing it all in red are stratovolcanoes that have erupted in the Holocene era, so roughly the last 12,000 years, with a volcanic eruption of VEI 6. So I'm picking out 6 different latitudes that are the triangles in black that do correspond to specific volcanoes, but this is not to say that it's a prescriptive experiment. That's just to pick a location that actually has a volcano to look at this. So we're not picking some random location that doesn't actually have a volcano present. And then we're doing the experiment for all of these 6 locations. So first, here is some of the results showing for an eruption at 42 degrees north in July of 2025. And what I'm showing you is the aerosol surface area density evolving over time for latitude here in the y-axis. And what we're seeing is that the aerosols stay mainly in the hemisphere of the eruption, and that there's a maximum aerosol amount roughly 2 to 6 months after the eruption. And that this, across all the latitudes, the aerosol surface area density goes back to like background after about 2.5 to 3 years. So one thing I forgot to mention is that all of these results that I'm showing you are relative of the volcanic scenario to the background non-volcanic scenario that I ran. So expanding this to look at some of the different latitudes, this top panel is the same as I just showed you. And we see that the tropical eruption leads to a globally widespread aerosol veil. And it seems to last for a bit longer. Maybe the intensity is not as high because it does get spread out more. And then another interesting thing is that on the southern hemisphere here, this is now a winter stratosphere. And this allows for the aerosols to spread across the 2 hemispheres. There's a few notes on this, that the injection height is kept constant in all of the experiments. So the higher latitudes and the winter tropopause will be different. So that also plays into it. And then there's obviously the thing that the northern hemisphere is not identical to the southern hemisphere. But we do see the same picture if I look at the January eruption, that then it would be the northern winter hemisphere that allows the aerosols to spread across both hemispheres. So looking at how long these aerosols will last in the atmosphere, a useful tool is looking at the E-folding time, which is the time it takes for the aerosol to decay to 1/E of the peak value. And what I'm showing you here is latitude versus E-folding decay time in months. And the different colors show some of the example of a subset of these experiments. So in black, I'm showing you sulfur dioxide only for a summer eruption. And then in blue, this is also SO2 only for a January eruption. And in red, I have a high co-injected halogen and going back to a summer eruption. And really what we see is that these error bars are showing the standard deviation of the ensembles, so essentially the ensemble spread. And there's really no significant change when you look at the specific latitudes. There's not really a significant difference between these. But what is significant is the change depending on latitude. So it doesn't really show a dependence on season or halogens. And which is, you can understand because the halogens don't really play a part in formation of aerosols. So that's a good test of the model as well. So now I want to look at what happens to ozone with all this volcanic aerosol present. So here in this case now we're looking at an injection at 58 degrees north. And the main panel here is now latitude versus time with ozone loss in red, as in column ozone percent change. And this is for an SO2 only eruption in July. I want to make a note that the scale here is not symmetric and it's also not in linear increments. So first we can see that the ozone loss is located in the northern hemisphere roughly at the same sort of time frame as the aerosols, which makes sense in this case. This also point here showing an increase in ozone on the opposite hemisphere to the eruption. And this is, a lot of that is due to transport. This was also observed after the Pinatubo eruption, that you had this increase on the opposite hemisphere. There has been a lot of studies trying to dig into exactly why that is. They usually give this answer of, it's due to chemistry and dynamics, which is kind of everything. So there's still some debate on exactly what contribution is from chemistry and what is from the dynamics. So it's definitely both comes into play here. So expanding this plot, so again, I have on the top panel here, I should say that, I have the average overall latitudes with the green shading representing the ensemble spread. And on the right panel here, I'm showing the mean overall time. Again, ensemble spread in green. And then what I have here in the corner are now 3-year averages for ozone loss, with the top being the northern hemisphere, the middle is global, and the bottom is the southern hemisphere. So we're seeing that if we look at the impact in different regions, we can see that from the plot already that we have a bigger impact on the hemisphere of eruption than we do on the opposite hemisphere. And this kind of evens out when you look at a global average. So then expanding this to all the 6 different latitudes that we investigated, one of the things that we can see from this is that the tropical eruptions tend to have a larger global impact than mid and higher latitude eruptions will have. On a global scale, where these higher latitude eruptions, they tend to have a higher impact in the regional level. And we also see this asymmetry present, and there's an interesting thing where we have the asymmetry of an increase in ozone and then followed by a decrease. And this we see, this decrease is more persistent for the winter eruptions, which is kind of an interesting feature, that it's this delayed impact that is then bigger for a winter eruption. You can see it a little bit here that this loss is not as persistent at this one, but really the true comparison is looking at the equivalent plot for the January eruptions. And it is true for that as well when we look at that. Then the next thing is then looking at halogen co-injection. So now I changed the color bar. We're still on an asymmetric scale with nonlinear increments. This panel here is the SO2 only, which is exactly this 42 north eruption that I'm showing here, just with a different color scheme now, with these yellows to purples as the ozone loss. And then the middle panel here, I'm co-injecting in intermediate amount of halogens. And then in the last panel, I have my high co-injected halogen scenario. And it's just, the first look is really obvious. With more halogens, you get more ozone loss. And in this high halogen case, it's really, like, this number goes up to somewhere around like 45% loss of ozone. All these changes are on top of whatever natural ozone hole might occur. And also for the high halogen case, the impact lasts longer than the 4 years of my figure here. So it really is quite dramatic when we have halogens co-injected. And you could say, well, on average, it's maybe not, like it's better if you live in the southern hemisphere in this case, definitely. But I think 80% of the Earth's population live like roughly at these latitudes. So this would be quite significant for a lot of people. So the last bit I want to show you is a little look at the seasonality. So what this plot shows is all of the scenarios that we looked at together. So this column here is the summer eruptions. The top is showing SO2 only scenarios. The middle is the co-injected halogen, and the bottom is the high co-injected halogen case. All of these are the 3-year averages for northern hemisphere, global, and southern hemisphere values, represented by the different colors. And they are, so there's 3 little bars for each of the 6 different latitudes, with the ensemble standard deviation in those little bars. And the first thing is really this high halogen case just stands out in bigger ozone loss than the other 2 cases. So that is really the main dependence, is the halogen co-injection. If I get this next slide up that it doesn't want to show, there we go. This column is now showing the winter eruptions. And again, we're seeing the same picture. It's hard to tell by eye from this plot if there's any changes. So we did a column that is the summer column minus the winter. So this means if I have positive numbers here, this means that a winter eruption leads to more ozone depletion or more ozone loss. And the overall is that you see this bottom panel here definitely shows more of an impact from changing the season, whereas the other ones, it's a little hard to tell with the standard deviation going on all over the place. And this is really the case, that the winter eruption leads to more ozone loss. Obviously, we already looked at some of the seasonality impacts that I showed you in the previous slides, but when you look at a 3-year average, some of those seasonality patterns, they do get washed out because you're averaging over several years. So there is some suggestion that there's some seasonality with the winter being more severe ozone loss, and also that but the main thing is really the latitude and the halogen content that impacts this. So now I want to change gears a little bit and talk about the Hunga Tonga-Hunga Ha'apai eruption. It happened on the the eruption I'm focusing on is happened on the 15th of January of 2022, and it was located here in the Kingdom of Tonga, and it's been classified as a VEI5 eruption. It was unprecedented in a lot of different ways. Here is a satellite image and an image from the Tonga Geological Survey. So they were sailing and took this image. And one thing that's cool here in this picture is that you can see the fuzzy layer here is the part of the cloud that stayed in the troposphere, and then the central bit here is all of the cloud that reached the stratosphere. Here's an image showing some of the volcanic lightning that was seen in the cloud. It exploded near a cyclone, and it's the largest eruption we've seen since 1991, Mount Pinatubo eruption, that coincidentally was erupting into a cyclone. That was an interesting point. It resulted in a tsunami and ash downfall in the main islands of Tonga. We had tsunami warnings on the US West Coast, also in Australia, and the waves here were like 1 to 4 feet. If I'll just remind you of how far away we are. So it makes more sense that there was an impact in Australia that's closer, but even on the US West Coast, this was experienced. And the pressure waves were felt all around the globe. It circled the planet a couple of times. Shock waves was measured around. The sound could be heard in Alaska and Australia. So it's really a really big deal. And the main thing that I didn't write down on this slide is that it went higher up in altitude than we have ever observed before. So part of the peak of this volcanic cloud reached up to 56 kilometers above the surface. So that's stretching across the stratosphere and dipping into the mesosphere. So it's even going out of the stratosphere. And some electronic signatures were also measured in the thermosphere. So it's really have a great impact. Looking at the sulfate from the SO2 from the eruption, here's the location of Hunga Tonga, and this image is from Tropomi, showing the amount of SO2 and showing the cloud being transported west. As I said previously, we're about 0.4 to 0.5 teragrams of SO2 in the cloud, and to compare with Pinatubo, that's roughly 5% of what Pinatubo was. There's some debate, maybe there was more SO2, but it was reacting or scavenged by water before it reached the stratosphere. So there's still some debate on that. The biggest deal about this eruption is that it injected an unprecedented amount of water into the stratosphere. It was about 150 teragrams of water, which is equivalent to 10% of the total stratospheric water content. So obviously this was on the southern hemisphere, so in this case that would be 20% of the southern hemisphere stratospheric water. And then also that the eruption reached up to 56 kilometers. Those are two of the main unprecedented observations from this eruption. So looking at the water, this is an image showing data from the microwave limb sounder instrument that's aboard the Aura satellite. And what I'm showing you here is a snapshot of the month of July for the pressure level of 26 millibars. And every point that I'm showing here is an observation that is above 7 ppm of water anomaly, like of water. And just to remind you, the background stratospheric mixing ratio is usually 4 to 5 ppm. So I'm picking a number that's already a bit above the normal background. And then what we see is that for July, it's really contained here all across. It's well mixed across the whole globe in the longitude band. And it's just everywhere at this point. So this is like 6 months after the eruption. And one thing you can sort of see, you can see the polar vortex forming here. So this is why there's not water. It's that little curve here. You can see that the water didn't actually enter the polar vortex. It's not like there isn't water on the northern hemisphere, but just not at this pressure level. So this is, yeah, that's just showing you how much this actually impacted. So I took some of this data. This is the MLS vertical profile at the location of Hunga Tonga. And then I scaled this profile to match my model vertical levels and used that as my injection profile. And I used 0.41 teragrams of SO2 and 150 teragrams of water to inject with that profile. I did some other experiments of having water only and SO2 only, and I'll get back to that to try to get some of the chemistry behind the impacts. I ran the model for 10 years with the eruption happening on the 15th of January. And like the other project I showed you, I did 30 model ensembles with varying the SO2 within the range of plus minus 1%. And I used the same climate scenario rather than using actual meteorology that I showed you before. So first off, this is what the water profile looks like if I look at 0 to 30 degrees south for the model outputs. And this blue line here is for February, then we've got March and April. And what the model's showing is that it removes the water too quickly, and this is also just moving it outside of the latitudinal band that I'm showing. It's not removing it from the model, but removing it from the area I'm looking at. And it's also moving it a little high too fast. But we can use the model too is we optimize that vertical profile so that we match the water for MLS, and then we can look at what is the mechanism behind all the other changes that we're seeing. So that's when I'm doing that and matching the water, then I actually get a pretty good agreement with the model versus MLS measurement. So this panel here is showing the MLS water vapor vertical profile, the water anomaly. And this is relative to 17 years of MLS measurements that are encapsulated by this little line over here. And then the anomaly for 2022 is in red. And my model water is shown here in the first panel. And the following species here in the panels here, so I've got the change in temperature, CLO, ozone, HNO3, HCl, and these are all observed by the MLS, and we're in a qualitative good agreement with what MLS is observing. Quantitatively, the HNO3 is too high. It's showing the right trend. So we're currently working on running some experiments trying to figure out that chemistry bit. And this would also lead to too big NOx and N2O5 losses. Yeah, so the reaction that leads that is the N2O5 hydrolysis, and there's some uncertainty on the gamma for this reaction, so that's where that's part of what I'm checking with the model. And then we can also see we have increases in HOX and HOCl. So the question now, based on the comparison to observation and a few species that we can output from the model, is what is then driving the chemistry? So now I did an experiment where I only injected SO2, and this is what I'm showing you here in red. So we're seeing we obviously don't have any water, and then the temperature is quite different. The CLO is roughly the same, so is ozone, HNO3, the NOx, and N2O5. So these things are mostly driven, the HNO3 and the NOx, those are mostly driven by the SO2 chemistry in this case. There's a very different HCl structure, and also the HOX and the HOCl are only partly described by the SO2. And the ozone is maybe a little bit towards more increases in ozone than losses compared to the full model. So if I add now lines for a water-only experiment in blue, now we see that the temperature is matching better what we were observing, and also the water is now here. There's some changes here that are due to some impacts of having the SO2 and the water together that changes the altitude. So that's what that is. For the CLO, there's a small contribution from the water-only case. And for ozone, it looks very different. And same as for these species where we saw that most of it was due to the SO2, we don't see a big impact from water. But for HCl, we see that this is really driving most of the HCl. There's some contribution from this really high altitude from the SO2. And then the HOX and the HOCl are now more of a combination. They're described by both things. So what we're seeing in the ozone profile is that we have this competition of the NOx and the CLOX and HOX cycles. So when we have less NOx, this will lead to an increase in ozone because we have less removal by NOx chemistry. So that is what ends up being the increase. But then for the lower altitude, we have an increase in CLO, we have an increase in HOX, so that both the CLOX and the HOX chemistry are increasing, which will lead to a decrease in ozone. So the resulting ozone profile is really the competition between these different cycles of ozone destruction. And then what we're seeing with the HCl is that it's really being driven by the water, which could be described by the O-singlet-D reaction with water that leads to increases in OH chemistry, and this will, further down the line, lead to the CLO increases and also this loss in HCl. So that's really what this is the stage we're at now with this, it's trying to describe the chemical mechanism behind these impacts. So finally, I want to show you a plot of the results versus time. So here I'm back to these latitude versus time plots, where on this left panel I'm showing aerosol surface area density, and on the right side I'm showing a stratospheric column water anomaly. And both of these are for the full model. And the aerosols are in really good agreement with observations when I look at it in the latitude versus time, but also in the vertical profile. We're in really good agreement with that. And the water, as I said, it moves the water maybe too fast out of the latitudinal band and maybe also too fast in time. But one thing we can see is we can see the polar vortex here, so that it is getting that right, that we didn't actually have the water enter the polar vortex in 2022. So it does get a lot of the things that was observed for 2022 right. So in summary, going back to the first project I showed you, we found a strong dependence on latitude and halogen content on the impact that we see on ozone following volcanic eruptions. And the dependence on season was a little bit more vague, but overall, the winter definitely leads to more ozone depletion than in the summer. And then a lot of the other seasonality dependencies are more detailed, looking at the first year after the eruption. The dependence on water from a volcanic eruption, we have pinpointed some of the impacts that are due to the SO2 and water individually. But you do really need to have the combination to get the full picture of what happened after the eruption. The water is more persistent in the atmosphere from observations than what the model is showing. So this is something that I'm investigating, the differences in the model dynamics, because it is getting the aerosols more or less right. So there has to be some differences in how it's treating water. And then I'm also looking at varying the amount of injected water to see if there's a sensitivity to the amount. And the initial results from that is that when you have more water, you get an increased ozone loss with more water. And then sort of my final little thought is that I want to look into the future and see what happens when the halogen background of the atmosphere is lower, and then what kind of impacts we would expect on ozone. And doing this with different climate scenarios to investigate the different possibilities. So with that, I'd like to thank everyone who worked with me, and also the SoCal modeling community that is always really helpful and open for discussions, and the funders. And here's a picture of the Anderson Group at Harvard. And thank you for your attention.
Thank you for a very interesting talk. Let's see if we have some questions from the room. Got one already. Very good.
Thank you for talk. It's very interesting result. I have two questions which are kind of off topic, but I was wondering whether there was any dependence on background meteorology, such as QBO phase, on the ozone response. And also, could you provide any insight for the ozone response in the polar stratosphere in following winter or spring? How much of this could be attributed to forced response compared to the internal variability of dynamics?
So for the first question, I'm prescribing the QBO in all of these. So I'm using an alternating QBO of year 2000 and 2001, and just alternating those for forever, essentially. The model has an option to generate a QBO if you increase the vertical resolution, but that comes with its own issues of, is it still right? For the Hunga Tonga project, a suggestion would be to look at previous QBOs and then pick a QBO that matches what the end of 2021 was, and then start from there to get a better representation. And then also using a nudged meteorology. That's also an option in the model that I haven't quite started exploring yet, but it's on my list of things that I want to do. So I haven't tested the changes in meteorology and what kind of impact that would have, because I am using the same QBO for all of these. So for that, there is an impact. I'm sure there is some impact, but I couldn't tell you exactly what. And then what? Can you repeat the other question?
Yeah, I was wondering about how much of this ozone response in polar stratosphere could be attributed to forced response. How large it is compared to internal variability of dynamics.
So you mean what's the interannual variability of the ozone holes compared to the impact from a volcanic eruption? There is some of it. So there is some of these changes, because I'm showing you the difference between a volcanic scenario and a background scenario. And some of the changes does average out when I'm doing my 30 model member mean. So some of that does get averaged out, some of the variability. But one of the things that the model does is that it might also change the timing of the ozone holes. So that could be part of what we're seeing, is this shift in timing. But yeah, that's.
Thank you. We have a question online. Thanks for the great talk. I have a question about the source of halogens content in the plume. Is it co-erupted with SO2 from the volcano, or it is natural oceanic emission of Cl and Br compounds like chloroform or bromoform that is attached to the plume from Beirut? Thank you.
Mm-hmm. Yeah, so this depends on. So if we talk about my example of co-injecting halogens, this would be in the form of HCl or 8Br, and those would usually be due from like the magma and the type of the volcano, the content of the magma. Is it basaltic or rhyolitic or all these different types of rock that you have in the magma? That can play a part in that. So that would be the sort of direct impact. If we were talking about the Hunga Tonga eruption, that was an underwater eruption. So some of the halogen that you could expect from that could be from the seawater, from the salt in the seawater. And there has been observations of BRO following the Hunga Tonga eruption, so there might be something. I don't have the seawater in my model, so I don't think the impact from Hunga Tonga would be that great, because I'm able to match what the MLS is observing, and I'm not including the sea salt. But that might be a feature that is probably relevant, but I don't think it's the biggest impact in this case. But it's not something that we have a consensus on, I think, at the moment, if it's exactly what it is from the Hunga Tonga eruption. But I think it is mostly like a volcanic and not like something attached to the plume, but it could be.
Okay.
Yeah.
Thank you. More questions in the room? Lieta is one.
Thank you for the great talk. I am just curious if you've thought about doing like periodic injections, and what are your thoughts about how, is it going to have like a cumulative change in ozone, or there is going to be like extra complications?
So you're thinking kind of like looking at solar geoengineering kind of experiments? Yes. Yes. So in my building, we're next to the Coich group, and they have a few students who are doing exactly that, using these periodic, and so are other people using the model to do that. And it does come with some issues, but usually you just get like a continuous, depends on how frequent your injections are, but usually the point of that would be to cool the surface, or like investigate how that whole process works, and if there's any complication with ozone from doing that, right? That's the big question. So if you're using sulfate aerosols, yes, there will be. Then you will reduce ozone, and then you just do it continuously. So it depends also on the amounts, because it does like depend on how much sulfate aerosol you generate. One of the students in the Coich group, he's using diamond particles. People are also using some calcium carbonate or different calcium particles, and they then don't have necessarily the same impact on ozone. So it's really looking at those different things and trying to figure that out. But it's not something that I'm doing personally, but people are definitely working on that.
Thank you. Any other question? Doug has one. How do I get there? Maybe pass it over. Thank you.
So in the first part of your talk, you talked about the injection of halogens, but there's really not that much evidence, is there, from observations that halogens have been injected from volcanoes? You had one example from a 2000 eruption.
Yeah.
What observations were used to measure that?
I don't remember that particular one, but there is a comprehensive study by Karn et al. Where they looked at satellite observations for, I believe, from about 14 years they looked for a period from 1978 to about 2000, and then of that, there was a period of 14 years of HCl observed from volcanic eruptions. These were all from smaller eruptions, but these were with different satellite instruments, one of which being Trupomi. So I think more it's the question of, we have observed it in smaller eruptions, and it's hard to predict when a volcanic eruption would inject a lot of halogen. Like, it's been observed in these historical cases that are studied by volcanologists who study the magmatic glasses and the trapped air in those glasses, and figure out, like, that's how we got the number from Mount Mazama, and there was also the Santorini super eruption in 1200s. that also had a lot of halogen in the eruption. So it's hard to tell when something like that would happen again.
And
But
it's also hard to tell if it gets in the stratosphere.
Yes.
Yeah.
Yeah, so it really depends on the eruption, on the explosivity, on the content of the magma, and it's hard to predict, and I'm not trying to predict that. So it's just really, let's hope it doesn't happen, I think, for us living here now.
Thank you.
Yeah.
Okay. Any other question online or in the room? Looks like we are done. Thank you so much for your great talk, and for the people here and online, see you next time. You'll receive an email when the next ACOM seminar will be. I'll keep you on your toes. Thank you.